Hi everybody, I'm really sorry about the technical issues I was having today. I just could not get connected to D2L. I'm going to have some backup measures in place, so hopefully this doesn't happen again. The good news is the examples that I'm going to do in this video are exactly like the examples that we did on Monday. And there were some harder problems that I was going to do, but actually I'm going to just cut those out, and I'm not going to ask you to be responsible for those at all, because I don't want to just make videos of those and not have you guys to be able to interact with me and ask questions. So I just won't make you responsible for those harder questions. Okay, one of the things I wanted to talk about with you guys today is the schedule. I got the impression that maybe not everybody had looked at the schedule and syllabus changes that I posted on D2L. First, let me really encourage you to take a look at that. There's a lot of important information in there. And so please take a few minutes to look at that. So on Monday, we talked about radiometric dating. The topics for when we're going to meet online are going to shift a little bit. So when we meet online and when I'm not going to ask you to meet online, that won't change. But the exact topics will, because I just didn't get as far on Monday as I'd planned. So I won't talk about nuclear weapons today. We're going to continue our discussion of radiometric dating. We should have met online today. On Monday, we will meet at the start of class time, and we'll do quiz 8. But that's all that we'll do together. For the rest of the time, I'd like you to use that to watch a documentary on the bombing of Hiroshima. Now, you don't have to watch it at that time. You can watch it anytime you want. I'll get the links to that posted on D2L tonight. The documentary is about 2 hours. Please be sure you watch the whole thing. What I'm going to ask you to do is to write a reflection on the documentary. And this is just kind of like a journal entry. I'm not looking for you to answer specific questions. I think there's a lot of powerful I don't know, information and interviews in there, and so I mean, I don't think you'll have any shortage of kind of writing what you thought about the documentary, what was interesting, what was horrifying, just kind of whatever thoughts or feelings you had about the documentary, write that in a reflection, and then I'll have a Dropbox for you to put that on D2L. And so on Monday we will meet in class for the quiz, but then once you're done with the quiz, you're free to go. And for the quiz, I am going to ask, if you can, to turn on your webcams so we can have the best transparency possible, and to try to reduce the temptation for people to use materials that they shouldn't. But I don't want to pressure anybody to do that that's uncomfortable with it. I know there are a lot of legitimate reasons why you might not be comfortable in turning on your webcam, or some of you may not have webcams. All I would ask you to do, if it's not going to be possible or for any reason to turn on your webcam, just send me an email. I don't need an explanation. Just tell me you don't have a webcam, or you're not comfortable with it. You don't have to tell me why. Or when we get there for the quiz, you can send me a private chat and say, you know what, you're not going to be able to turn it on. That's fine. Just let me know. If you don't contact me, I am going to ask that you please go ahead and turn on your webcam. Then next Wednesday, we will meet for online class, in person, if you will. Then the following week, I'm going to again ask you to watch some documentaries and some films. And so the week of April 20th to 25th, we will not meet in person for the online class. However, I will be logged in at that time, so that's a great time. If you have questions or concerns, or you want to talk to me or go over problems, that would be a fantastic time to do it. So you do not have to meet either of the days that week, but I will be logged on to answer any questions anybody has. And then the last week of classes, we will have an in-person meeting at the time of the class. And we'll take quiz 9, sort of the same procedures as quiz 8 as far as the webcams. I would appreciate it if you can turn it on, and I'm going to ask that you do, but don't feel pressured if there's any reason you can't or uncomfortable with it. I just need you to, or I just ask that you please let me know. And then the last day of classes, we'll meet again for the online meeting, but that time will be devoted to taking the makeup quizzes. And so you don't have to let me know which quizzes you want to make up now. Sometime the week before, I can get that information from you. And as far as I know, the final exam is set for Wednesday, May 6th from 1 to 2:30. If anything changes on that, I'll be sure to let you know. All right, the other table that I wanted to draw your attention to, and again, this is posted in the schedule and syllabus changes that's posted on D2L. I have the due dates and times for all the remaining assignments this semester. So the radiometric dating worksheet that I sent out last night, as I said, that's going to be due this Sunday at 5 p.m. Your reflection on the Hiroshima documentary will be due next Tuesday by midnight. Then I'll also ask you to write a reflection on the bomb documentary. That'll be due the following Tuesday. We'll have some videos on nuclear energy, and I'll ask you to do a reflection on those. And then there will be a couple worksheets, and I'll ask you to write a reflection about nuclear fusion. And so all the due dates for those are listed here, but I just copied and pasted this from the file I posted on D2L that has the changes to the syllabus and the schedule. Okay, so let's get into radiometric dating. And so this is just really an application of the decay rates that we were doing last time. So one of the most common and well-known types of radiometric dating is carbon-14 dating. And that's the one that I'm going to talk about specifically. And I'd like to explain how that works. And to start that explanation, we need to talk about cosmic rays. So we've encountered cosmic rays before briefly when we were talking about the biological effects of radiation and what some natural sources of ionizing radiation are. And we are all exposed to cosmic rays. What they are is they're ultra-high energy particles that are produced in outer space. We're not actually 100% sure where they all come from. A small amount come from the sun, but actually most of them come from outside of our solar system. The speculation is that they are some remnants of supernova explosions, or they may also be coming from the giant black holes that make up the cores of most galaxies. Now, the name cosmic rays is actually a little bit of a misnomer. They're not actually rays, right? When we say rays, that kind of implies electromagnetic radiation, but they're not. In fact, they're very fast-moving particles, sort of the same idea as alpha particles and beta particles, right? What makes them dangerous is that they're moving so fast. And what makes up cosmic rays are about 1% high-energy electrons, and so that's kind of like beta particles, but most of it is heavier things. And they're nuclei that have been stripped of all their electrons. So there's a lot of protons, a lot of helium-4 nuclei, and a lot of other stuff. And cosmic rays are so high in energy that when they hit the atoms that exist in our atmosphere, they literally blow those nuclei up, right? They smash them into many pieces. They're essentially breaking them up into their constituent protons and neutrons. And so that requires a tremendous amount of energy. So that gives you an idea of how much energy is contained in these cosmic rays. Now, another important fact about cosmic rays is the flux, or the amount of cosmic rays that are hitting the Earth at any given point in time, is relatively constant. And that's important for carbon-14 dating to work. All right, so what the heck does cosmic rays have to do with using carbon to date objects? Well, the cosmic rays are what ultimately produces the vast majority of carbon-14 on the planet. And what happens is when the cosmic rays hit stuff in the atmosphere, it busts them up into the constituent subatomic particles, right? So what makes up nuclei are protons and neutrons. And so when those cosmic rays hit an atom in our atmosphere, it busts it up into the protons and the neutrons. Well, those neutrons that are produced can then smash into other atoms in the atmosphere. And by far the most common element in our atmosphere is nitrogen. And so one of the likely reactions that happens as a result of these cosmic rays is the neutrons they produce smash into nitrogen. And it causes a transmutation reaction. And that transmutation reaction produces hydrogen 1s, but the key is what else it also produces. And so if we balance this nuclear equation like we've learned in the past, we can see that on the left-hand side, the mass numbers add up to be 15, And then we have the 1 on the product side. So to make this side equal to 15, I need a 14 in the mass number of the missing thing. And if we do the same thing for the atomic numbers, right, there's 7 on the reactant side. We get 1 from the hydrogen, so the missing piece has to be 6. And so if you look at our periodic table, element number 6 is carbon. And so what makes the cosmic rays important is that they're what makes the carbon-14 that exists on Earth. And what happens then is, another common constituent of our atmosphere is oxygen. And so when this carbon-14 is produced in these nuclear reactions, it can then undergo chemical reactions with the oxygen and turn it into carbon dioxide, right? And we know that plants absorb carbon dioxide. And so anything that, breathes in or absorbs carbon dioxide, when it takes that carbon dioxide in, some of it is going to contain carbon-14. And so that radioactive carbon-14 that's produced by the cosmic rays gets incorporated in the plants. And then when other organisms eat the plants, the carbon-14 moves from the plants, obviously, into the thing that ate it. And then if other things eat the things that ate the plants, right, they also get the carbon-14 inside of them. And so what ends up happening, because the flux of cosmic rays is relatively constant, and because the decay of carbon-14 is regular, so it's constantly being produced in the atmosphere as more cosmic rays hit, but it's constantly being depleted as the radioactive carbon-14 decays. And so what happens is we've essentially come to an equilibrium. So the amount of carbon-14 is essentially relatively constant, because it's constantly being produced and added more by the cosmic rays, but it's also constantly being used up. And so the net effect is the total amount of carbon-14 in living organisms doesn't change. As long as you're alive, as long as you're a plant and you keep absorbing carbon dioxide, as long as you're eating plants or eating things that eat plants, you're constantly replenishing the carbon-14 as it decays. And so for all living things, the level of carbon-14 is constant. But what happens is when you die, or when something dies, you stop incorporating more carbon-14 into the body of that organism, and so the amount of carbon-14 starts to decrease because it is radioactive. And so we know how much carbon-14 is in a living thing, and so if we can measure how much carbon-14 is in a dead thing, like an artifact or bones or a carcass or something that was made from wood, we can determine how long ago that thing died based on how much of the carbon-14 it's lost. Now, we do know that the flux of cosmic rays is not 100% constant, and so there can be variations in the level of carbon-14 at any given time. And so what scientists have done is they've calibrated radiocarbon dating techniques to other techniques that we know we can use to determine the ages of things, but it doesn't work for everything. So, for example, we've used rings in trees. Certain species of trees live to be very old. We can look at ice cores, where we get sort of a new layer every season, so we can determine the age of ice cores, or by sedimentary deposits in geological formations. And so to really calibrate our carbon-14 dating technique and to make it even more accurate, we can use it in combination with other dating techniques. All right, so let's get into the examples. And as I said, there's no difference between these examples and the ones that we did on Monday. It's just that all of these examples specifically deal with carbon-14, whereas in the other case, we were dealing with different isotopes. But the work is exactly the same. And so the two equations that we're going to use are exactly the same. So we have NT equals N0 e to the minus KT. And then we know that the rate constant is related to the half-life by 0.693 over the half-life. When we were given the amounts of the radioisotopes, and so we would use those for N0 and NT last time, we had mass, we used becquerels, we used curies. the most common way to specify the amount of carbon-14 in something is with the activity, and the units they use is disintegrations per minute per gram of carbon. So anytime you see this disintegrations per minute per gram of carbon, they're telling you the activity, and so that's either the NT or the N0. The amount of carbon-14 in living organisms, that's always going to be the N0, and it's basically constant, and so you don't have to have this number memorized. I'll always give it to you, but you'll notice in all the problems, we always use the same value. The amount of, or the activity of carbon-14 in living things is 15.3 disintegrations per minute per gram of carbon. Right? The NT is what the activity of carbon-14 is in the object that we're testing. And so it's always going to be less than 15.3 because, right, this is what it is when the thing is alive. When it dies, it immediately starts decaying until we test it and see how much activity of carbon-14 there is. So in this problem, again, oftentimes you want to start by asking what do they want the final answer to be. And so when I see in the statement of this question, they want to know how old this skull is, right? Then effectively they're asking me about the time. I want to solve for time. So we're looking for the time. Right, we said the activity of carbon-14 in living things is 15.3. And the activity of carbon-14 in the artifact that we're testing, that's always going to be NT. And so we also need K, but we'll find K the same way we did in the examples that we did on Monday. So we'll find the rate constant based on its relationship to the half-life. So to get the rate constant, all I have to do divide that by the half-life, and I get 1.21 times 10 to the negative 4. And if you wanted to write the units, they would be in 1 over years. All right, but now I have all the information I need to solve the problem. So we'll go back to our main equation. And so we'll plug in NT, plug in N0, negative K, and we're solving for the time. All right. Now, whenever I start doing the algebra on these, one of the things I like to consider is, am I going to have to use the natural log to get rid of the exponent? And in this case, because the time, the variable I'm solving for, is in the exponent, I am going to need to use the natural log, right? But first I've got to get the e and its exponent by itself, so I've got to get this 15.3 over to the other side. So I'll divide both sides by 15.3. And when I do that, on the left I get 0.294. All right, and so now I can take the natural log of both sides to get rid of that e. And the natural log of 0.294, I get minus 1.22. All right, and to finish it off, and so for t, I get 10,114. And then be sure we always have to put the units because they gave us the half-life in years, right? The time and the half-life have to have the same units. So the units on my time are going to be years. Okay, here's another example. And I just noticed this example's lacking a little bit of information. We're talking about carbon-14 dating, so it's kind of understood. But what I should have said, what should its carbon-14 activity be in disintegrations per minute times gram today? All right, so it may seem like we don't have enough information to solve this problem, right? They told us that the deer died 975 years ago, so the 975 years, that's time, but they didn't give us any more information. And actually, I did this on purpose because I wanted to point out that the half-life of carbon-14 doesn't change. So in the last problem, we were also using carbon-14, and the half-life was 5,730 years. So the half-life is still 5,730 years. And the activity of carbon-14 in living organisms, that is basically a constant. So that doesn't change either. So I also know that the N0 is 15.3. Now, I'm not going to ask you to have these memorized. I just wanted to do this example to point out and stress that these things are constants. The level of carbon-14 in living things is a constant, and so if we had it in the last problem, we can use it again in this one, and the same thing with the half-life. And in fact, we already calculated K. That's not going to change either. We know that's 1.21 times 10 to the minus 4, 1 over years. And so we can use those bits of information from the last problem to solve this one. But like I said, I won't do this to you on a quiz. I think it's important to point out that the level of carbon-14 in living things is a constant, and the half-life is a constant. So that's why I didn't put it in this problem, so we could specifically talk about this. But in problems I give you on a test or a quiz, I'll tell you the activity of carbon-14 in living things, and I will specifically tell you the half-life in that problem. You don't have to have these memorized. Okay, but so in this problem, if they want to know what the activity of carbon-14 is today, right, they're asking for the NT. So they want NT. Right, we know N0. We calculated K in the last problem, and they gave us the time, so we can plug everything in, and we have everything except for NT. All right, and we don't have a variable in our exponent. Those are just numbers, so I'm not going to have to worry about taking the natural log this time. The NT is already by itself, so I just have to evaluate this. So you can plug that whole thing into your calculator. I'll break it up into 2 different steps in case that helps some people. So we have NT is 15.3, and then when I do e to the negative 1.21 times 10 to the minus 4 times 975, I get 0.889. And then when I multiply that out, I get 13.6, and the activity is going to be in disintegrations per minute per gram of carbon. So we can abbreviate that if we want. We can do disintegrations per minute times gram. All right, now this is the last example that was on the original slides that I was going to go through, but because we can't meet in class and you can't ask questions, I thought I would do a couple more examples in case people wanted to see some more of those, since you couldn't ask me directly. But if you do have questions, don't hesitate to send me an email or a text and reach out to me, and we can set up a time to meet to go over whatever questions you have. All right, so in this problem, we're told a tree is chopped down today and it's made into a wooden chair. And I want to know how long it will take for the carbon-14 in the wood to decay to 8% of its level when the tree was alive. And here I've gone back to what I would give in a normal problem on a quiz. I'm not making you get the half-life of carbon-14 from the last problem, although obviously it didn't change. And so in the 2 previous examples, we were using the activity of carbon-14 in disintegrations per minute per gram, but we don't have to. Just like any other isotope, we can specify the amount of carbon-14 however we want. And so, like some of the examples we did on Monday, here they're representing the activity with the percent. If you remember from those examples, anytime they give us the percent, they're basically giving us the NT. And then we can assume that the N0 is 100. So when they are talking about the amounts of a radioisotope in percents, the percent that they're giving you is the NT, and the N0 is therefore 100%. So when I see those percentages, I immediately think, oh, they're giving me NT is 8, and N0 is 100. Right? And so I wrote that down even without thinking about what they're asking me for. So now when I go back to look at the problem, and I'm like, all right, what am I solving for here? Right? I notice how long will it take? Right? So that's telling me that they want me to solve for the time. And so, right, in our main equation, we have NT equals N0 e to the minus KT. Right? We know NT, we know N0. As is common in most of these problems, they didn't give us the rate constant, but they did give us the half-life. So I can use that K is 0.693 over the half-life. And so if I plug in our actual values for this problem, and I know we did this in the previous example, but I wanted to show out all the steps in case anybody was having questions. All right, and so now I know NT, N0, and K. That should be 1 over years. And so I can plug those in, and we can solve for T. So I have 8 equals 100. All right, and we see that the variable we're solving for is in the exponent. So I am going to have to use the natural log. But I got to get rid of this 100 first. Right, now I can take the natural log of both sides. The ln and the e will cancel. When I do the natural log of 0.08, I get negative, nope, I get negative 2.53. Right, we'll divide by the negative 1.21 times 10 to the minus 4. And so for T, I get 20,874. And again, because the half-life is in years, the time has to be in the same unit. And so the units on my final answer are years. Okay, and let's do one more example. Okay, so here we're told that samples of the Dead Sea Scrolls were analyzed by carbon dating, and it was found that the carbon-14 present had an activity of 11.9 disintegrations per minute per gram. And we're given the activity of carbon-14 in living things, and we want to know how old are the Dead Sea Scrolls. And I can see, right, normally I would have told you the half-life of carbon-14 is 5,730 years. Right, so I will give you that in the statement of the problem. You don't have to have that memorized or anything. And so when I think about what they're asking me to do, right, when they ask me how old something is, they're asking me for the time. So I'm solving for the time again. So NT right, the activity of carbon-14 in living things is N0. The activity of carbon-14 in the dead things is NT. So they gave me NT, they gave me N0, right? We're looking for time. I need the rate constant, so we'll do that like we've done in all the other examples. We'll use K equals 0.693 over the half-life. And so, again, all right, we can plug everything in. So NT is 11.9, and 0 is the 15.3. All right, we're solving for time again. It's in the exponent. I'll have to use the ln, but again, I've got to get rid of the 15.3 first. And I get 0.778. All right, so now we're ready to take the natural log of both sides. And when I do the natural log of 0.778, I get negative 0.251. All right, to get t by itself, again, I have to divide by the 1.21 times 10 to the minus 4. And when I do that, I get 2077, so the Dead Sea Scrolls are about 2,000 years old. Again, the half-life was given in years, so the time has to be in years. All right, so that's my last example on carbon-14 dating. Again, if you have any questions, please don't hesitate to reach out, and we can set up a time to meet with Blackboard Collaborate and go over some problems together. And so the last thing I wanted to mention is carbon-14 dating is not the only type of radiometric dating. There are lots of other isotopes that are very commonly used. And the examples that I was going to do, if I hadn't had the technical issues, is I was going to talk about uranium and lead dating. And that's actually kind of cool. I have some videos on this. They're in the file that has the video list. If you're interested, you might want to take a look. I'm not going to make you responsible for that at all. I'm not going to ask you to do any of those calculations. But the way we're able to do those, that type of dating is actually kind of cool. And actually, the age of the Earth that we understand to be about 4.5 billion years old primarily comes from that type of dating technique, as well as other isotopic dating techniques. All right, so that's the end of the video for today. I hope you all have a good rest of your day.